Hey everybody, this is John Buck back with another array signal processing video. In this video we're going to talk about plane waves and homogeneous media. Plane waves are important because they are the fundamental building block that we use mathematically to think about array signal processing. To make an analogy, when we think about signals and systems in a time domain class, the complex exponential is the fundamental building block, right? We use the Fourier transform to think about a time domain waveform as a superposition of complex exponentials, all at different frequencies that are weighted by different amplitudes and phases. And that Fourier's big idea was that we could build any interesting practical signal out of this superposition of complex exponentials. But then that lets us think about one exponential at a time, how a given system reacts to one exponential at a time. The same type of logic applies in array signal processing for plane waves, that we'll think about any wave field, any scalar field, as a superposition of plane waves of a single frequency and a single propagation direction. And that we can think about how the system responds to one of those at a time, and then build up the story as a superposition of those. And so that same underlying idea applies the same way in linear systems. We show that complex exponentials are eigenfunctions of any LTI system. The equivalent for the array signal processing story is to show that a plane wave is an eigenfunction for the wave equation for waves propagating in homogeneous media, for scalar waves propagating in homogeneous media. So that's the big picture of where we're going today, to show that a plane wave satisfies the wave equation, and to think a little bit about that. And then as we move forward in the class, we'll be looking at how do we think about plane waves as the basis for all the other things we're going to do in the class. And also an important practical application in their own right. It's not just theoretical, but there are a lot of times in array signal processing where we're interested in the signals arriving as plane waves. And we'll say more about that as the class goes on. But let me stop the video intro here and switch over to the whiteboard. Okay, so again, our topic for today are plane waves and homogeneous media. We're going to assume that f sub p of t is a scalar field, where p is the position vector. So our usual scalar coordinates, p is x, y, and z in Cartesian coordinates, and then t is our time vector. Sorry, time value. And we're going to now look at the special case where we say we assume that our field contains a single propagating plane wave, so a plane wave at a single frequency with a single direction or wave number vector. So in that case, we're assuming that fp of t has a specific form. So it's a complex exponential, e to the j, and then the quantity of omega t minus k vector dot p vector. Where, again, p is our position we just saw, and k is the wave number vector. Okay, so which has three components in the x, y, and z directions: k sub x, k sub y, and k sub z. And so what we're going to show is that under the right condition, that propagating through homogeneous media, that this is a solution that is an eigenfunction. That is, it just propagates unchanged, and it is a solution to the wave equation. We'll see later then, for single frequency signals, that we can build any complicated wavefront as a weighted superposition of these plane waves. So the next thing to do is, maybe I'll start this on a new page, or maybe scroll down, and get the wave equation here to remind us what the wave equation is. And again, just in case, this is a dot product if you're not familiar. So we're saying it's the inner product or dot product of this vector with the position vector. So we'll write that out in a minute, but let me get the wave equation up here first. So our wave equation for homogeneous media says that del squared times f, or del squared of f, is equal to 1 over c squared, where c is the speed of sound, or general speed of the phase speed of propagation, times the second derivative, partial derivative with respect to time of f. Right? And remember, del squared is just a way to say the second derivative of all the frequencies, all the spatial directions together. Right? So I can expand that out. Right? And del squared is just shorthand for second partial with respect to x, plus second partial with respect to y, plus second partial with respect to z. So if we now want to evaluate this, we want to first maybe plug in to our plane wave equation, bring our plane wave back here. And before I apply del, the first thing I'm going to do is, or to plug it into the equation above, I'll do it on each side, but I'm also going to use properties of exponential to factor this into two pieces. Looking ahead, I'm doing this because I see on the left side of my wave equation, I'm going to be doing spatial derivatives. On the right side, I'm going to be doing time derivatives. So having those as two separate terms will make it a little easier to see how things work out here. And then I'm going to write that last term out. I'm going to expand out that inner product to make it explicit where the x's and y's are. Okay, so when I do that, the k dot p vectors becomes k sub x times x plus k sub y times y plus k sub z times z. So now I'm ready to plug this in to each side of the equation and solve for them separately. And I think I'll do that on a new page. Let me get set up for that. So again, with our assumed plane wave solution, showing that this is a propagating solution, I'm going to first solve, I'll do the right-hand side with the time domain first, because it's a little easier. So I want to find 1 over c squared times del second derivative with respect to t of f. Right? And when I do that, it turns out because my partial derivative is with respect to t, everything in the second term in the product here, right, that I'm just pointing at right here. Oh, I didn't want to move that. I just wanted to point at it. No. Right, everything in this product, or in the second term doesn't matter. So I'll get a 1 over c squared, and then the second derivative of this from the chain rule, I'll bring down a j omega squared. Right, so I get that j omega squared, and then everything else remains the same because it's an exponential, right? I'm taking the derivative with respect to t. This is why I got these out of the chain rule, but I still have the exponential, and everything in the second exponential doesn't matter at all. And I can simplify j omega squared as just minus omega squared. And then everything to the right is still fp of t, so I'm going to rewrite it like that. Okay, so that's one side of the wave equation. Now we're turning my attention to the other side. I'm going to do the del squared of f, which is, as we wrote a minute ago, is just the sum of all the three partial derivatives of the different Cartesian coordinates. Right? And plugging in for f, I get this. And so now when I look at this, if I take the second partial with respect to x, I'll get the same as I got before, just working on the other term. I'll ignore the e to the j omega t because it has no x dependence. The chain rule will tell me I get a minus j kx quantity squared down in front. And the minus j squared will become just a j squared, which is minus 1. Similarly for ky and kz, each one of those terms will bring down a k squared with a minus sign in front. So let me bring all that down from my chain rule. Right, and so now, again, everything on the right over here, right, all this material here, oops, didn't mean to actually draw on that. All this material here is still just f, and this becomes a minus kx squared, a minus ky squared, and a minus kz squared. So I can just factor all that out. Right, and I've shown that I pulled the minus sign out front. I get kx squared plus ky plus kz squared times the original f of pt. Right, and so now if I go back to the previous page and remind myself, well, those are just the sum of the squares of the three components of k. So if I take the sum of the squares of the three components of a vector, I'm just finding the magnitude squared of that vector. So I can go back to that page and rewrite this term here as just the magnitude squared of k. So let me do that. So again, now I've got to simplified all this to say the del squared just becomes a minus magnitude of the k vector squared times f of pt. I've now got the two sides of the wave equation and I can put them together. So let me make some space to do that. And when I do that, right, I have my left side, the del squared became this minus norm or magnitude squared of the k vector f of pt, and I have minus omega squared over c times f of pt. Right, so now I've got that f on both sides, I can cancel out. And what that leaves me with then is that, and we're getting rid of the minus sign on both sides, is I have a minus norm k squared is omega squared over c squared. right? And so this is the common, we've seen this definition like in an electromagnetics or an acoustics class, that the norm squared of the wave, if I take this to its logical conclusion, that the norm of the wave vector, the magnitude of the wave vector, is the radiant frequency divided by the speed of propagation. And so that is showing that the wave equation is satisfied by this plane wave, because this is our usual definition of how we get this, right? K might have the kx, ky, and kz terms that are the projections of the k onto the three Cartesian axes. But this is the main point that we want. Now, in the Van Trees book, one of the things this will often do is they'll then use this approach to rewrite the wave vector k as its magnitude, omega over c, times an a vector, where this a is a unit direction vector. So in doing it, it sort of factored the wave number vector into two pieces. The first one here is the magnitude of the vector is omega over c, so it depends on the time radian frequency, or 2 pi f over c if you like, and the speed of propagation. And then the other term that's about the direction, to keep those separate. And that's a strategy we'll see is helpful, to have these sort of normalized things so we can think about how frequency affects it or how direction affects it separately. So coming back to what that means for the wave equation, if I go back to my original equation for my plane wave here, right? Another way to think of this is, what will happen if I have where will I have the lines of constant phase? And the lines of constant phase will be points where as t increases, I need k dot p to increase by the same amount, which for a given k vector is just anywhere, right? It's going to move along that k vector, and at any point, I'll have a constant wavefront of all the points that are orthogonal to k. So let me sort of sketch that, and we can interpret that a little bit as we finish up. Right, so our wavefronts are the set of points where omega t minus kp remain constant. If I imagine taking a snapshot, if I freeze time at an instant, as I just said a second ago, the wavefronts will be the set of points perpendicular to k, the set of p's that keep the inner product the same, which are all the lines perpendicular to k. So imagine I'm sort of looking from above, I can sketch that. So here's my wave vector, or wave number vector. Right, so I'll have my wavefronts are a point of, or for a given value of phase where k dot p is constant, are these blue lines here. And those blue lines are separated, if I sort of imagine this as like looking from above in a map, those blue lines are separated by the period in space, which we call the wavelength, or lambda. Okay, so we have these sort of things that are for a snapshot in time, which is like taking a picture with your phone. So if it helps to have this image, we could imagine looking at a picture of a wavefront. So here we have a picture of a bunch of waves coming into a beach. This is from the Wikipedia Commons. Mike Pennington gets the photo credit for this. I'll put that in the notes for this episode, for this video as well. And this is the Easting Beach in the Shetland Islands, apparently. A place, a part of Scotland I've never visited, but I hope to someday. And so you could imagine these are like the wavefronts here to make this. Oh, it's not drawing as well as I'd hoped here. So by taking this picture, we've frozen a moment in time, and here's our wavefronts. We can see the breaking wavefronts coming into the beach. These would be spaced in a mathematically ideal version, lambda. But this is a very evocative image to help you think about what these wavefronts are, even though they're not, and the problems we'll study, these are going to be often, we think of them as like compression waves in underwater acoustics, or they could be electromagnetic waves if you think about an array of sensors there, and not necessarily physical waves. But we can see these, and they give an excuse to show a beautiful picture of a beach. So I wanted to bring this in. Conversely, if I think the other way, I could think about freezing a point in space, which is what I do if I put a sensor there, and then I have time running, and so I'll have a time waveform going past. So if I fix my location in space, then what I'm just looking at, instead of an overview like this overhead map I show here above, is just a classic waveform like we see in signals and systems class. Right, and when I do that, t is now my variable, p naught is fixed, and I just see for a single frequency a waveform oscillating path. Looking like this, and again the distance between the peaks that are not very well drawn here would be my period in time, capital T. And that sort of is the first of a lot of analogies we see, that wavelength in space is the analogy of capital T, the period of a periodic waveform in time, when I have these single frequency plane waves propagating in a single direction. So I'll wrap up here. There's plenty to this video. It took a little longer than I thought, but it's an important idea that we'll keep coming back to, that single frequency, single direction plane waves like this are eigenfunctions of the homogeneous wave equation, and they are the fundamental building blocks we'll use to build up the picture in space the same way we build things up in time, one frequency at a time with complex exponentials. In array processing, we'll be building things up or thinking about them one plane wave at a time. Okay, so I'll stop here and I'll see you next time.